We now take up the last major topic of this course. The subject is intractable problems. These problems are decidable, but colloquially they are said to be problems that take at least exponential time as a function of their input size. The reality is a bit different, but they are problems for which there is an overwhelming amount of empirical evidence that these problems take exponential time, although no solid proof of that belief. If a problem does take time that is exponential in its input size, then that means it can in practice only be solved for small instances. Suppose to be concrete that the time it takes to solve an instance of size n is 2 to the n. Then doubling the speed of machines makes essentially no difference in how large an instance you can solve. It adds 1 to the size n that you can solve in a fixed amount of time. Using 1,000 machines instead of 1 has the effect of adding 10 to the size n. And using 1,000,000 machines, each 1,000 times faster than today's machines, adds 30 to n. You never get to really big sizes of problem instances that you can solve. As a result, it is generally accepted that in order for a solution to a problem to be considered usable in practice, it has to run in less than exponential time, and in particular in polynomial time for some large polynomial. While an algorithm that runs in some large polynomial time, like n to the 1,000th power, is no more practical than one that runs in time 2 to the n, we find in practice that if a problem has a polynomial algorithm at all, then it has an algorithm that runs in some low-degree polynomial like n squared or n cubed at the most. In this lecture, we introduce several important preliminary concepts. We introduce the idea of a Turing machine that is time-bounded. It can only run for a time that is a known function of its input size before it has to stop and tell us whether it accepts or rejects. We introduce the class P of problems or languages, it's the same thing of course, that can be solved by a Turing machine that runs in polynomial time as a function of its input size. We also meet the class NP, which is problems that can be solved by a Turing machine that is non-deterministic, but has a polynomial time bound along each branch. Finally, we'll learn about polynomial time reductions, which are reductions where the transducer runs in time that is polynomial in its input size. These are used to show one problem intractable by reducing a known intractable problem to it. We say a Turing machine is T of n time-bounded, where T of n is some function of n, like n squared or 2 to the n. If given an input of length n, the machine always halts in at most T of n steps. Okay. We allow the Turing machine to have several tapes. In some circumstances, we allow the Turing machine to be non-deterministic, although in that case we will specify that it is a T of n time-bounded, non-deterministic Turing machine. Also in that case, we mean that any sequence of moves of the non-deterministic machine is no longer than T of n. In practice, a deterministic multi-tape Turing machine is close to the idea of an algorithm that runs in time proportional to T of n, or big O of T of n. That is, while some algorithms take longer on a Turing machine, even multi-tape, than on a real computer, these are rare. Moreover, when there is a difference, the difference tends to be small. A Turing machine M is said to be polynomial time-bounded if it is time-bounded by any polynomial. It could be linear, quadratic, cubic, or n to the 1,000th power, as long as it is some polynomial. The languages that are accepted by polynomial time-bounded Turing machines form the class P. Now, P is defined formally in terms of Turing machines, but it could just as well have been stated as polynomial time on a real computer. The reason, which we address on the next slide, is that if an algorithm runs in some polynomial time on a computer, then it will run in polynomial time on a multi-tape Turing machine, or even a one-tape Turing machine, although the degree of the polynomial may be higher in some cases. That is, we saw a way to simulate a name-value store by a computer. That is the part of a real computer that takes the most time when simulated by a Turing machine. But if a computer runs for on the order of T of n steps, then it can't store or retrieve more than T of n items in its memory. A Turing machine can simulate one lookup or insert into a name-value store in a number of steps that is proportional to the length of the tape that holds the store. But that length is proportional at most to the number of steps the computer has taken, which is T of n, and thus the Turing machine takes at most T squared of n of its own steps. If T of n is a polynomial, then so is T squared of n. The The exponent grows, of course. A cubic algorithm on a computer might take time proportional to n to the sixth on a Turing machine, but it's no worse than that. And since we're trying to divide the world of problems into those that have polynomial algorithms and those that don't, we can think Turing machine or computer, whichever is more convenient. As you might expect, when simulating a program, it's best to simulate a Turing machine. But when devising an algorithm, it's best to think about a computer program. Here are two examples of problems or languages, which is the same thing, in the class P. For each context-free grammar G, there is an algorithm, the CYK algorithm, that takes an input string W and tells whether W is in the language. The running time of this algorithm is O of n cubed. The second problem I want to talk about is finding a path in a graph. Here we're given a directed graph that is a list of its nodes and arcs. We are also given one node as the source node X and another as the sink node Y. The answer is yes if there is a path in the graph from the source to the sink. Graphs must be coded in a finite alphabet, which should not be hard to see. Represent the ith node by n followed by I in binary, and represent an arc by a pair of nodes, the tail and the head of the arc. Use two special symbols to indicate the source and sink nodes. Note that if there are m nodes, it takes order log m space to represent one node, so n, the input length, is actually somewhat greater than the number of nodes and arcs, but the difference is unimportant since we are only worrying about polynomial versus not polynomial. Depth first search answers this question in time that is linear in the number of nodes and arcs. On a Turing machine, you might need order n squared steps, since for one step of the depth first search, you have to locate on the input the arcs with a given node as the tail. That could require that you run all along the tape just to simulate one computer step, but n squared is still a polynomial, so as far as membership in P is concerned, n squared is just fine. And just to make sure, when we talk about polynomial time, we include every running time that is less than some polynomial. That is, the definition of P only requires that the language be accepted by some Turing machine whose running time is bounded above by some polynomial. For example, there are many algorithms that run in times like order n log n, but that's less than n squared, so the problems solved by algorithms like this are surely in P. Before proceeding, I want to examine in detail a problem that seems to be in P but really isn't, and I want you to understand why. This is really important in understanding what the class P really means. The problem called knapsack is this. We're given a list of n positive integers. The answer to this instance of knapsack is yes, if and only if we can partition the integers into two groups whose sums are equal. For example, if the integers are 1, 2, 3, and 4, then I can partition them into 1 and 4 in one group, and 2 and 3 in the other group, and the sums in each group will be equal. Incidentally, the problem is called knapsack because of the view that the integers are weights of items, and two hikers want to divide the items between their two knapsacks so each carries equal weight. At first glance, we can solve the knapsack problem by a polynomial time dynamic programming algorithm. That is, we maintain a table of all the differences in sums we can achieve by partitioning the first j-1 integers. When we incorporate the jth integer, we take each possible difference and both add and subtract the jth integer, thus getting two new possible differences. After looking at all integers, we see if 0 is a possible difference. To be more precise, for the basis we consider none of the integers. Then the table has true for 0 difference and false for all the other differences. For the induction, suppose we have a table for the first j-1 integers. We build a new table to reflect the partitions of the first j integers. Initially, each entry in the new table is false. But suppose the jth integer is I sub j. For each difference m that was true in the old table, set the entries for m plus I sub j and also m minus I sub j to be true in the new table. Let's compute the running time of this algorithm as a function of the sum of the integers. Let's say that sum is s. We need order s space to construct a table for one value of j, since the differences must be in the range minus s to plus s. And it only takes order s time to construct each table from the previous one using a real computer. Maybe it's order s squared on a Turing machine because we have to move the head a long distance to write each entry. But again, when designing algorithms and worrying only about whether something is polynomial time or not, a real computer is the right model to think about because the programming details are generally easier. Okay. Note that n is equal to or less than s since the integers are each positive. That is, the sum of the integers is at least equal to the number of integers on the list. Thus, we can build a table that corresponds to the set of all the integers in order s squared time, s for each of n different tables. We then look in this table and see if 0 is true. If so, the answer to the knapsack instance is yes, and otherwise it is no. However, that conclusion is actually deceptive. Although it is true that we just described an algorithm that runs in time no more than the square of the sum of the integers, and that algorithm really does solve the knapsack problem, it doesn't tell us that the knapsack problem is in P, and in fact it is almost surely not in P, as we shall see later. The reason this algorithm doesn't show knapsack to be in P is that membership in P requires that the algorithm runs in time polynomial in the input size. But we can't just define input size to be the sum of the integers in the input. The input size is always the number of cells it takes to write the input on a Turing machine tape. For the knapsack problem, this input length is not necessarily polynomial in the sum of the integers, as we shall see on the next slide. The longest input length occurs if we have n integers, each of whose values is about 2 to the n. If we write the integers in binary, the input to the Turing machine is order n squared in length. But a table then requires about n 2 to the n entries and at least that much space to write down. That is, the sum of all n integers can be around n times 2 to the n. We can't construct one table in time less than its length, so the total time of the algorithm is on the order of n squared times 2 to the n. But the input size is n squared, and n squared 2 to the n is not a polynomial function of the input length. By the way, we usually like to have n be the actual input size for the Turing machine. So if we substitute n for n squared, we can say the inputs of size n leads to an algorithm that takes time proportional to n times 2 to the square root of n. That is still not a polynomial. Thus, the dynamic programming algorithm we described, while it is really a good algorithm when the integers are of limited size, does not show the knapsack problem to be in the class P. There is another problem which we can call pseudo-knapsack. The question is the same, but the integers are represented in unary, not binary. That is, integer I is represented by I1s followed by some marker symbol to separate integers. This problem is in P, and the dynamic programming algorithm proves that. But it is not the classical knapsack problem where integers are represented in binary, the sort of rational way to represent large integers. The second important class of languages for our story is NP, the non-deterministic polynomial class. NP is defined in terms of non-deterministic Turing machines. The running time of a non-deterministic Turing machine is the maximum number of moves it takes along any branch. That is, by making any sequence of choices. If there is a polynomial bound on that time, then the non-deterministic machine is said to be polynomial time bounded. And the language or problem it accepts is said to be in the class NP. For example, the standard version of knapsack, where integers are represented in binary, is an NP. The non-deterministic polynomial time algorithm that solves this is fairly simple. First, it uses its non-determinism to guess a partition of the integers into two subsets. This can be done in time that is linear in the input length using 2 extra tapes for the 2 subsets. Then sum the subsets and compare. Say yes if this partition yields 2 equal sums, and this part can surely be done in time that is quadratic in the input size and can be done in linear time if you're clever and use a few extra tapes. Thus, standard knapsack is an NP. Note that this fact doesn't suggest a deterministic polynomial time algorithm, since it may take exponential time to simulate the non-determinism of the Turing machine. Are P and NP really the same class of languages? That is, can any problem that is solved by a non-deterministic Turing machine in polynomial time also be solved by some deterministic Turing machine in polynomial time, even if the degree of the polynomial was higher? This question was posed by Steve Cook in 1970. At first, it didn't seem all that hard or unlikely. After all, non-deterministic finite automata can be simulated by deterministic finite automata, even though the number of states might grow. And deterministic Turing machines can simulate non-deterministic ones. But the problem has proven to be very, very difficult, and mathematicians who once sneered at the question and assumed it was easy because computer scientists had thought it up, now recognize it as one of the most important mathematical questions, perhaps the most important unsolved question. However, there are thousands of problems that are in NP, but for which no algorithm in P has been found. And unfortunately, neither is there a proof that these problems are not in P. What we do have is a linkage of the large class of problems called NP-complete problems, which we discuss on the next slide. What we do know, then, is that either all these problems are in P or none of them are. So they mutually enforce the notion that none of them are, since many have been worked on for decades and no polynomial time algorithms for any of them have been found. So we're going to address the question of whether P equals NP by identifying complete problems for NP. Say a problem in NP is NP-complete if the following is true about the problem. If the problem is in P, then P equals NP. That is, every problem in NP is also in P. It turns out that almost every problem that is known to be in NP but is not known to be in P is NP-complete. There is only one well-known exception, graph isomorphism. Given two graphs, is there a one-to-one matching of nodes between the two graphs that makes the graphs identical? This problem is known to be in NP. Just guess the matching of the nodes in the two graphs and check that the right edges exist. But there is no polynomial time algorithm known, and neither is there a proof that graph isomorphism is NP-complete. But graph isomorphism is an exception to what appears to be an almost general rule. If it is in NP and it isn't known to be in P, then it is NP-complete. While the definition of NP-completeness merely states that there has to be some way of proving P equals NP from the assumption that the problem is in P, there is a standard way of making such proofs, and it appears to be sufficient for all the NP-complete problems that we know about. This method involves reductions of the type we talked about for Turing machines in general, but with the condition that the transducer run in polynomial time as a function of its input size. Intuitively, a complete problem for a class embodies, in some sense, every problem in the class. For example, post-correspondence problem embodies every Turing machine, even though it is hard to see PCP as involving computation. It seems to be about concatenating strings in constrained ways. So it might surprise you to know that each NP-complete problem, such as knapsack, embodies all non-deterministic polynomial time computation, even though the knapsack problem seems to be about anything but computation. So in order to show problem L to be NP-complete, we have to show that every problem in NP is somehow embedded in L. We need a transformation from every problem in NP to L, and this transformation has to be sufficiently fast that if we had a deterministic polynomial time algorithm for L, then we could use it to build a deterministic polynomial time algorithm for each problem in NP. We're going to define a polynomial time transducer. Notice that people frequently shorten polynomial time to polytime, and we'll start doing that too. So a polytime transducer is a deterministic Turing machine that takes an input of length n, runs for some polynomial number of steps p of n, and produces an output on an output tape. It is important to observe that although we do not restrict the output length, since the Turing machine only runs for p of n steps, it could not write more than p of n symbols. Thus, the length of the output of a polynomial time transducer is always polynomial in the length of its input. Here's a picture of a polytime transducer. It can have any fixed number of tapes. One is the input tape and one is the output tape. We argued on the last slide that the output length must be polynomial in the length of the input, but the real constraint on the polytime transducer is on how long it runs. It is not acceptable to have it run for time that is exponential in its input length, even if the output is short. Consider two languages or problems, say L and M. We say L is polytime reducible to M if there is a polytime transducer T that takes an input W that is an instance of L, produces an output X that is an instance of M, and the answer to L on W is the same as the answer to M on X. That is, W is in L if and only if X is in M. Here is a picture to help us remember what a polytime reduction does. On the left is the set of strings over the alphabet of L, divided into those that are in L and those that are not in L. On the right is the set of strings over the alphabet of M, also divided between M and its complement. In the middle is the polytime transducer T. Every string in L is transformed by T into a string that is in M. There can be strings in M that are not the target of any string in L. And every string not in L, but over the alphabet of L, is transformed by T into a string that is over the alphabet of M, but is not in M. Again, there can be strings in the complement of M that are not the target of any string in the complement of L. Formally, we say a problem or language M is NP-complete if, first of all, it is an NP, and for every language L in NP, there is a polytime reduction from L to M. An important consequence of the fact that M is NP-complete is that if M has a polytime algorithm, then so does every language L in NP. That is, the classes of languages P and NP are the same, or P equals NP. Notice that earlier we suggested that the definition of NP-completeness was simply that the language had this property. Steve Cook's original definition of NP-completeness was exactly that, and it is often referred to as Cook-completeness. Cook concentrated on showing one particular problem, the question of whether an expression of propositional logic was satisfiable, that is, made true by some assignment of truth values to the propositional variables. But shortly after Cook wrote his original paper on NP-completeness, Dick Karp wrote another paper that showed many of the classical problems that had been puzzling mathematicians, sometimes for centuries, were NP-complete. Karp used only polytime reductions from the problem Cook had proved NP-complete. Since then, it is generally accepted that the preferred definition of NP-completeness is the one we gave here, the existence of polytime reductions. To make the distinction, this notion of NP-completeness is often called Karp-completeness. So here's the plan for proving certain problems to be NP-complete. Here's all of NP. SAT, the satisfiability problem for propositional logic that we just discussed, is one problem in NP. Cook's theorem is that every problem in NP reduces in polytime to the SAT problem, so SAT is the first known NP-complete problem. Cook also proved a restricted form of SAT called 3-SAT to be NP-complete by reducing SAT to 3-SAT. We'll learn what the 3-SAT restriction is shortly, but in brief it is SAT restricted to expressions that are the AND of clauses with 3 literals per term. A literal is a variable or a negated variable, and a clause is the OR of literals. Then from 3-SAT we do polytime reductions to many other problems, either directly or indirectly. Each problem we can reach from SAT by a chain of polytime reductions is thus proved NP-complete. But before we embark on this quest, let's make sure that polynomial time reductions work in the sense that they let us draw the desired conclusion about all of NP reducing to the target problem. So suppose M has a polytime algorithm, say running time Q of n for some polynomial Q. Let there be a polytime transducer T from some problem L to M. And let the time taken by T be P of n for some polynomial P. The output of T, given an input of length n, is at most of length P of n. So when we run the algorithm for M on this input of length P of n, the algorithm takes time Q of P of n. Note that a polynomial of a polynomial is a polynomial. The degrees of the polynomial are multiplied, but it's still a polynomial. We claim there's a polytime algorithm for L. Given an input W of length n for L, apply the transducer T to W. The result is an output X of length at most P of n, and more importantly, T takes time only P of n to produce this output. Apply to X the algorithm to tell whether it is an M. As we observed on the previous slide, this part takes time Q of P of n. Then return as the answer for W whatever the M algorithm says about X. The total time of this algorithm is P of n plus Q of P of n, which is polynomial if P and Q are. It is a correct algorithm because the fact that T is a polytime transducer from L to M says that the answers to input W and output X are the same. In this lecture, we're going to prove one problem, satisfiability for Boolean expressions, to be NP-complete, by showing how to reduce the language of any non-deterministic polytime Turing machine to satisfiability. We will then cover two of its restricted versions called CSAT and 3SAT respectively. We'll learn shortly what those mean. Our first step is to learn about Boolean expressions, or what is the same, expressions of propositional logic. These expressions consist of constants, variables, and the operators and, or, and not. There are only two constants, true and false, which we'll usually represent by 1 equals true and 0 equals false. The variables can only take on these two values as well. The operators and, or, and not have the usual logical meaning. When we write these expressions, we'll use concatenation, that is, no operator symbol for and. So xy really means x and y. We'll use plus for or, so x plus y means x or y, and we'll use the minus sign for not, so minus x really means not x. Here is an example of a Boolean expression. X or y is true when at least one of x and y is true, and not x or not y is true when at least one of x and y is false. So the whole expression is true when at least one is true and at least one is false. Since there are only two variables, that means exactly one is true and exactly one is false. As for any kind of expression, remember to use parentheses to alter the order in which operators are applied. The order of precedence is not first or highest, then and then or. Thus, the parentheses in the example expression are needed to make sure that the ors are applied before the ands. A truth assignment is an assignment of 0 or 1, that is false or true, to each of the variables of a Boolean expression. In general, the key question about Boolean expressions is which truth assignments give them the value true. But for our NP-complete problem, we need only this very simple question: given a Boolean expression, does there exist at least one truth assignment for which the value of the expression is true? So this expression is satisfiable. There are, in fact, two satisfying assignments, those that make one of x and y true and the other false. But this expression, x and not x, is not satisfiable. There are only two truth assignments. X can be assigned true or it can be assigned false. If x is true, then not x is false. That is, the and of expressions, one of which is true and the other is false, has value false. Similarly, if we assign x false, then x is false while not x is true, and the and of these is again false. We must see the SAT problem as a language, just like all the other problems we've discussed. First, the instances of the SAT problem are all the Boolean expressions. Since expressions can have any number of variables, we must code expressions in a finite alphabet. The parentheses, the plus and minus, can represent themselves, but we need to have a scheme for representing variables. We'll represent the ith variable by the symbol x followed by I in binary. So here is an example of an expression coded this way. We've assumed that x is the first variable, so it is represented by an x followed by 1. That appears here and also there. Y is the second variable, so it is represented by x and 2 in binary, that's x, 1, 0. What we call the variables doesn't matter as far as satisfiability is concerned, so we could have called y the first and x the second. Generally, the easier part of proving a problem NP-complete is proving it is an NP. Generally, you just guess a solution and then in polynomial time you check it. The SAT problem is no exception. Okay. Well, we need to describe a non-deterministic Turing machine that can take a coded Boolean expression as input and tell if it is satisfiable. And of course, the non-deterministic machine must be polynomial time-bounded. In this case, order n squared time suffices. The power of non-determinism lets us guess a truth assignment. We'll use a second tape to write down the guess of a truth value for each variable. Then, in the expression itself, replace each variable by its guessed truth value. We can now evaluate the expression bottom-up. The non-deterministic machine accepts if the value of the expression with this assignment is true. Notice the power of non-determinism here. The number of assignments could be exponential in n, the length of the expression, but the non-deterministic machine works on all the expressions sort of in parallel, thus appearing to finish in time that is polynomial in the input size, because we only count the time taken for processing one single assignment. Also, notice that non-determinism is more than parallelism. Given any fixed number of processors, say 1,000, we could divide the time needed to evaluate the effect of each truth assignment into 1,000 groups and evaluate them in parallel. But if there are 2 to the n assignments, it would still take each processor time 2 to the n divided by 1,000, which is still exponential in n. We're now going to give the proof of Cook's theorem that the SAT problem is NP-complete. Since we don't have any NP-complete problems yet, we can't do a reduction from some one other problem to SAT. Rather, we have to show how to reduce any problem in NP to SAT in polynomial time. We do these reductions by assuming nothing about the problem L that is an NP, except that it has some non-deterministic polynomial time-bounded Turing machine that accepts L. To make the reduction from these Turing machines to SAT easier, we're going to make some restrictions on the Turing machine, but only restrictions we can assume without losing any of the problems in NP. That is, every problem in NP has one of these machines, which we'll describe on the next slide. The restrictions we make are the following. First, that the non-deterministic machine has only one tape, and that the head never moves left of its initial position. We'll assume the states are never also tape symbols, so we can tell which symbol in an ID is the state. Point 3 clearly loses us nothing, since we can always change the names of the states without changing what the machine does. And we've already seen the constructions many tapes to one and two-way infinite tape to one way. Each of these constructions can square the number of steps the Turing machine makes, but that's okay. The square of a polynomial is still a polynomial. This slide has a collection of random but important comments about what we assume about the non-deterministic polytime Turing machine M, in addition to the restrictions we assumed on the previous slide. First, let P of n be the particular polynomial upper bound on the running time of M. We'll be simulating M on an input W, which is of length of n. This next assumption is really about how we define the next ID relation. We're going to assume that if M accepts W, then there is a sequence of exactly P of n moves from the initial ID with a final state in the last ID, and perhaps other IDs as well. We're going to assume that if M is in an accepting state, then the identical ID represents one legal move. So if M enters an accepting state early on, then the sequence of IDs leading to acceptance can be extended to length P of n by repeating the first ID that has an accepting state. There is no harm in doing this. M is already accepted, so entering an accepting state more than once will not change anything. And this is an observation rather than an assumption. Remember that the head cannot move more than P of n squares and P of n moves. So we're going to represent each ID by a sequence of exactly P of n plus 1 positions, the first P of n tape squares and the state. Initially, most of these are blank, but it's okay for some of these p of n plus 1 positions to hold a blank beyond where the head has reached so far, even if this blank is not technically part of the ID. We have to design a polytime transducer that can turn the input w into a Boolean expression that is satisfiable if and only if m accepts w. The transducer is designed knowing m but not w. The first thing the transducer does, seeing w, is to determine its length n. The expression that is output from the transducer will involve p of n plus 1 all squared, what we call variables. But these variables are not the propositional variables of Boolean logic. Rather, they are collections of propositional variables that together represent the symbol in a particular position of a particular ID. That is, the variable we'll call xij represents the jth position of the ith ID. Thus, I and j are each in the range 0 through p of n inclusive. Think of the variables arranged in an array. The rows represent successive IDs, and the columns represent positions in those IDs. We'll start with the initial ID, with the start state, input w, and the rest of the positions blank. We'll design the expression to be satisfiable if and only if m accepts w. We'll see that the expression constrains the values of the variables so that the only way the expression can be satisfiable is if each ID represents a move from the previous ID, or the previous ID has an accepting state and the next ID is the same. And the expression also requires that the state in the final ID, I sub pn, is an accepting state. Thus, from m, which it knows, and w, which it sees, the transducer constructs an expression. Any satisfying truth assignment for this expression will give the x's the proper values that form an ID sequence of m with input w, leading to acceptance. Now remember, the x's are not Boolean variables. They represent states and tape symbols of m. However, each variable can take on only a fixed number of values, the sum of the number of tape symbols and the states of the known Turing machine M. Thus, we can represent each xij by this number of propositional variables, exactly one of which can be true. That is, for each state or tape symbol A, let y sub ija, that's this, be a propositional variable, and we want y sub ija to be true if and only if x sub ij equals a. As we describe the construction of the Boolean expression, we must make sure that we take time that is only a polynomial in n. There are many components from which the final expression is built, but they fall into two classes. Some depend on w and therefore depend on n. These components are and must be of size that is a polynomial in n. And more importantly, we can write them easily so that the time taken to write them on the output is polynomial in n. The second kind is those that depend only on m. These take a constant time as far as input size is concerned. That is, m may have lots and lots of states and lots of tape symbols, but these quantities are independent of n, so as far as we're concerned, they're all just constants. And to make our lives a bit simpler, don't forget that if an expression has a set of arguments whose size is fixed independent of n, then no matter how large the number is, it is a constant as far as n is concerned. So the time to write any such component is a polynomial in n. In fact, it's a 0th degree polynomial. Now let's start to describe the output of the transducer. The output is an expression, and we want it to be satisfiable if and only if m accepts w. The whole expression is the AND of 4 sub-expressions, each of which enforces one of 4 conditions. First is the sub-expression we'll call unique. It enforces the rule that there is only one symbol in each position of each ID. That is, the value of xij is unique. The second sub-expression is starts right. It forces the initial ID to be the start state followed by w. The next is moves right. This really should be moves correctly, but that's too many syllables. This expression enforces the condition that each ID follows the previous ID by one move of m. And as that convenient exception, if the previous ID has an accepting state, then the next ID may be the previous ID. Finally comes the expression finishes right. This condition says that somewhere in all that stuff is an accepting state. For unique, we use the AND over all IDs I, positions j, and states or tape symbols y and z of the expression not y sub ij capital Y or not yij capital Z. This little expression is satisfied as long as at most one of the two Boolean variables yij cap y and yij cap z is true. Put another way, if xij were to have two different symbols, say cap y and cap z, then one of these little expressions would be false. But unique is the AND of all these expressions, and the entire expression is the AND of unique and the other expressions. Thus, the entire expression cannot be satisfied by any truth assignment that makes any pair of variables yij and yij both be true. Now let's formulate starts right. This expression requires the first ID to be the one m starts in with input w. Let w, whose length is n, consist of symbols a1 through an. We want x00, the first position of the first ID, to be the symbol that is the start state of m. That's used conventionally q0. And we want the next n variables to represent w. That is, x0i must be ai for all I up to n. And all the other positions of the first ID are blank. That is, x0i is blank for I between n plus 1 and p of n. But there's a propositional variable for that. Each of the conditions that makes up starts right is of the form some one of the x variables is a particular symbol. But that's what the propositional variables yija do. So we can write starts right as the AND of y sub 0, 0 q0 and y 0, 1 a1, the first symbol of w, and y 0, 2 a2, and so on, and after, let's say, y0 n an, then you got to have y0 n plus 1 comma blank, and so on. So finishes right is easy. M accepts if and only if the last ID has an accepting state, because once M enters an accepting state, it appears to stay in that state until the ID numbered p of n. So take the OR of the Boolean variables y sub p of n, j, and q, where q is an accepting state and j is anything from 0 through p of n. Now let's see how long it takes to write down the three of the four expressions we have described. Remember, we have yet to describe the hard one, moves right. Unique is actually the most time consuming. It requires that we write down big O of p squared of n symbols. The p squared comes from the fact that we range over all I and j between 0 and p of n. The constant factor comes from the fact that for each I and j there are a large but finite number of pairs of states and or tape symbols, each of which needs a little expression. The number of pairs may be large, but it is independent of n, so it is a constant. And that expression involves two parentheses, three logical operators, and two propositional variables, only a constant number of things. But let me remind you again that the real issue is not how long the expression is, but how long it takes to write it. But the expression is simple, and it is simple to write the expression by looping on I and j, thus taking time proportional to its length. Starts right is the AND of p of n propositional variables, and again the pattern is simple, so we can write this expression in order p of n time. The same holds for finishes right. There are p of n propositional variables, and we need to output those variables connected by ORs. Oops, I lied. The running times are a little larger than I said. Not enough larger to take us out of the polynomial class, but larger by a factor of log n. That is, I cannot really output a propositional variable like y sub ija in one step, or even a constant time, the reason is that we have to use a finite alphabet to represent order p squared of n propositional variables. We agreed to represent a variable by the symbol x followed by an integer in binary, like this. To represent order p squared of n variables requires integers whose length is order log n. But this is no big deal. A factor of order log n is less than a factor of n, so all it can do is raise the degree of a polynomial by 1, not even that much. So in what follows, we're going to ignore factors of log n and just assume we can write down a propositional variable in constant time and space. We're now going to start working on moves right. A lot of this expression simply says that xij equals xi minus 1j. That is, a symbol in the ith ID is the same as the symbol in the same position of the previous ID. That will be true whenever the symbol in that position is not the state, and neither are the positions to the left and right in the previous ID the state. Since a state can only move one position, we know nothing changes two or more symbols away from the state. So we're going to construct one sub-expression for each I and j saying that either xij equals xi minus 1j, or the state is lurking about. The idea that the state is lurking is the or of those propositional variables y sub I minus 1 k a, where k is within 1 of I and a is a state symbol of M. Now we need to translate the equality of xij and xi minus 1j into propositional variables, but we just need the or of yija and yi minus 1ja, that's this, for all symbols a. The reason that works is that we already have unique to enforce the condition that for only one symbol a can yija or yi minus 1ja be true. The expressions we constructed for each ID I and position j will be part of moves right. Each says colloquially that the tape symbol can't change if the state isn't nearby. They will be ANDed together with expressions that enforce the correctness of the moves of M for the case when the state is nearby. To write the expression for moves right, we need to consider both the case on the left, where a position holds a tape symbol, and so do its neighbors to the left and right, and the hard case on the right, where the state is nearby. In the easy case, there is no doubt that the symbol in position j of the ith ID is the same as the jth symbol of the I minus first ID. We already covered this case in the previous slide with the expressions that say if the state is not nearby, then the symbol doesn't change. But in the hard case, there are three positions, the positions that hold the state in the I minus first ID and its neighbors that can be affected by the move. Moreover, since we're simulating a non-deterministic Turing machine, there may be a choice of move, and we need to coordinate the three positions in the ith ID to make sure that all three reflect the changes of a single choice of move. For the hard case, the pieces of the moves right expression must do two things. It has to pick one of the possible moves of M, that is, a state of Q, a tape symbol A, and a direction, that is, the choice of one of the triples in delta of Q and A. And then, for that move, it must enforce the condition that when the jth position of the ID I minus 1 holds the state Q, and the j plus first position of the I minus first ID holds a symbol A, then in the ith ID, the positions j minus 1 through j plus 1 reflect that move. Note that either the j minus first or the j plus first position is unchanged, so the expression also has to enforce the condition that this position is unchanged from the previous ID. That is, suppose delta of QA contains, perhaps with other choices, a leftward move going to state P and writing B over the A. That would be that. Then, for any IDI position J and tape symbol C, that is, this is ID I minus 1, that's I, This is position j minus 1, that's j, and that's j plus 1. Okay. Then one possibility for the 6 variables represented by this rectangle, that is this, is the combination that is reflected here. That is, P has moved, the state has become P has moved to the left. The C is unchanged, but its actual position is different. And the A has been replaced by a B. Similarly, if the move is to the right, that is something like that, then the 6 values are the ones we must enforce for the variables in this rectangle. And those, well, the C doesn't change at all. The state Q becomes P and it moves to the right. So it's here, and then the A got replaced by B, and the B appears over here. Now we can assemble the parts of moves right that enforce the moves. We already gave the formulas that say if the state is none of x I minus 1 j minus 1 through x I minus 1 j plus 1, then xij equals x I minus 1j. That is, you can't change a symbol if the state is not nearby. Now we have to include expressions that constrain the 6 variable x's that are near the state in the I minus first ID. For each possible move, write an expression for each position j and each ID I that expresses the constraints on the 6 relevant x's for that move. There is one more type of move of M that isn't really a move. We need to allow no change in ID if M is an accepting state. For each accepting state of M, there's a fake move in which nothing changes. For each I and j, take the OR over all moves of M of the expression you just wrote for I and j. Now, for each I and j, you have an expression that says the 6 relevant x's reflect some move of M. Take the AND of these expressions over all I and j. Also include in the AND all the expressions from earlier that say symbols don't change if the state is not near. Okay, there's a small glitch in all this material. We assumed position j was not 0 or p of n, the leftmost and rightmost positions that are represented by the IDs. If j is one of these, there are only 4 x's involved, and we need to modify so that the missing symbols are assumed blank. The same fix-up is needed for the rules that say the symbol doesn't change if the state is not nearby. If the symbol in question is at one of the n positions 0 or n, then there is no possibility that the state is outside this range, and we can omit that requirement. Now consider how long it takes to write down the moves right expression. Moves right consists of the AND of 2 p squared of n expressions, 2 for each ID I and position j. One of the 2 is the expression that says the symbol doesn't change if the head is not nearby. The other says that if the head is nearby, then the 6 relevant symbols are related in such a way that they reflect one move of M. Each of these expressions can depend on the number of states, symbols, and moves of M, but none of this depends on n. That is, as far as the length of the input W is concerned, each expression is of constant size. We claim that each of the order p squared of n expressions is easy to write down in time proportional to their length by a transducer that knows the moves of M. So the transducer can output moves right in time that is polynomial in the length of its input W. As always, there is another factor log n because we must write the Boolean expression in a fixed alphabet, but factors of log n cannot take us out of the polynomial class. So, to sum up the proof of Cook's theorem, it takes time less than order p cubed of n for the transducer to output the Boolean expression that is the AND of the 4 key components: unique, starts right, finishes right, and moves right. We claim that this transduction really is a polytime reduction of the language of M to the language SAT. First, if M accepts W, then there is some ID sequence that leads to acceptance. Imagine the P of n plus 1 by P of n plus 1 matrix of the xij's. The accepting sequence of IDs lets us fill out this table correctly, giving the value to xij that reflects the sequence. The expression we constructed will be satisfied when we assign to the propositional variables yijA the truth values implied by this choice of xij's. So if M accepts W, then the expression is satisfiable. Conversely, if we have a satisfying assignment for the expressions, we can get unique values for the xij's from the propositional variables. The unique expression assures that the xij's can be given unique values. And starts, finishes, and move right assure us that the xij's form an accepting computation of M with input W. That is enough to show that every polytime non-deterministic Turing machine's language is polytime reducible to SAT. We now have one problem, SAT, that we know to be NP-complete. We're going to reduce it to other problems in order to show them NP-complete as well. But it is easier to polytime reduce a special case of SAT called 3SAT to other problems. So our first step is to show that SAT is NP-complete even if the Boolean expression is in a very special form. The first restriction that we place on expressions is that they be in CNF, that is conjunctive normal form. These expressions are the AND of clauses, and a clause is the OR of literals. And a literal is either a propositional variable or its negation. So our next step will be to show to be NP-complete the problem CSAT, which is whether a Boolean expression in conjunctive normal form is satisfiable. Here's an example of a CNF expression. The first clause, this, is X or not Y or Z. That is, X, not Y, and Z are each literals. The second clause is just this, not X. That's okay. A clause can be the OR of only one literal. The third is the OR of four literals, which are not W, not X, Y, and Z. Okay, we're not going to reduce SAT to CSAT. Rather, we'll examine Cook's proof and see where it needed to be fixed up to make the output expression be in conjunctive normal form. That way, we will have a direct reduction of every problem in NP to CSAT. Okay. Everything but moves right is already in CNF. You can review the constructions, but when you do, you'll find that unique is the AND of clauses. So is starts right. In fact, each clause has only one literal, which is in fact an unnegated variable. And finishes right is the OR of unnegated variables and therefore is a single clause. Now let's look at moves right. It is the AND of an expression for each I and j, where I is an ID number and j a position in that ID. Recall this expression says that either the head is not near position j and the symbol in position j of ID I is the same as the symbol in the same position of the previous ID, or the head is at position j in the ID I-1 and the three symbols of ID I around position j reflect one move of the polytime Turing machine M. Here's the subtle thing. As complicated as these expressions are, they depend only on M and not on the input length N. As a result, we can write the expression for a given I and j in conjunctive normal form. It is possible to convert any Boolean expression to conjunctive normal form. I'll show you the trick on the next slide. This conversion does, in the worst case, exponentiate the length of the expression, but it doesn't matter in this application because the only expressions to which we need to apply the conversion are expressions whose size is independent of the input length n. Thus, the time taken to convert to CNF for each expression is just some constant, independent of n. Here's how we'll convert a given Boolean expression to CNF. We'll consider each truth assignment that makes the expression false. Note that if there are k variables in the given expression, there could be 2 to the k such truth assignments, and the resulting expression will take that much time to write down. But again, we're only exponentiating a constant, and the result is still independent of the input size n. For each such truth assignment, we construct one clause. If variable x is assigned true in this truth assignment, then the clause has literal not x, and if x is assigned false, then the clause has literal x. That way, the only time the clause, which is the OR of all of these literals, is false, is if this is the exact truth assignment. The resulting CNF expression is the AND of the clauses for each truth assignment that makes the original expression false. Thus, the CNF expression is made false exactly for those truth assignments that make the original expression false, and therefore it is of course true exactly when the original is true. For example, consider the expression not x or y and z. This expression is made false by three truth assignments, those in which x is true and at least one of y and z is false. Let's convert the first truth assignment, where x and y are true and z is false. Here is the resulting clause. Since x and y are assigned true, the clause has not x and not y. Since z is assigned false, the clause has z without negation. Notice that the only way to make this clause false is to make each literal false, which means giving each variable its value from the truth assignment that generated the clause. The other two truth assignments generate the next two clauses, this and this, and the entire CNF expression is the AND of the three clauses. It is therefore made false exactly when the variables are given one of the three truth assignments. A Boolean expression is said to be in K-conjunctive normal form, or KCNF, if it is the AND of clauses, each of which contains exactly K literals. The problem KSAT is whether a KCNF expression is satisfiable. For example, the expression we derived on the previous slide, which we show here, is in 3CNF. Notice it is the AND of clauses, and each clause has exactly three literals. We're going to prove that the problem 3SAT is NP-complete. The easy part, as is often the case, is that 3SAT is an NP. We already saw that the general problem SAT is an NP. Just guess a truth assignment and check that it makes the expression true. Since 3SAT is a special case of SAT, the same non-deterministic algorithm works for 3SAT. We're going to prove the NP-completeness of 3SAT by polytime reducing CSAT to 3SAT. We might suppose that the way to do that was to find a polynomial time algorithm to convert every CNF expression into a logically equivalent 3CNF expression. But not only can you not do that in polynomial time, you can't do it at all. That is, there are Boolean expressions that simply have no 3CNF expression. I'm not going to prove that formally, but an example is the expression with four variables that is true if and only if an odd number of the variables are true. That is, exactly one or exactly three of the four variables are true. Fortunately, the reduction does not have to preserve equivalence of the input and output expressions. Since we are dealing only with whether expressions are satisfiable, all we need to preserve as we transform the input expression to the output expression is that either both are satisfiable or neither is. Thus, we're going to give a polytime reduction that does not preserve equivalence. In fact, it doesn't even preserve the set of propositional variables. Rather, it introduces new variables into clauses that have more than three literals in order to split them up into many clauses of three literals each. So, consider a clause with k literals, x1 through xk. Remember, these are literals, not variables, so any of the xi's could be not followed by a propositional variables. We need k minus 3 new variables, which we'll call y1 through yk minus 3. These y's appear in no other clause, and they're really variables, not literals. Also notice that if k is equal to or less than 3, then no new variables are introduced. We're going to replace the clause x1 through xk by k minus 2 clauses. The first consists of the first two literals, x1 and x2, and the first new variable unnegated, that's y1. The second, which is this, has only one of the original literals, x3, and two variables. The previous variable, y1, is negated, while the next variable, y2, is not negated. That pattern repeats. Each new clause has one of the original literals, say that, a negated previous y, and an unnegated next y. Then finally, the last of the new clauses has the last two of the original literals and only the previous y negated. We need to show that when we make this change, the new expression is satisfiable if and only if the original expression was. For the first direction, we'll show that if there is a satisfying truth assignment for the original expression, then we can extend this truth assignment to also provide truth values for the y's that will make the and of all new clauses true. So suppose that there is a satisfying truth assignment for the original expression. Then this assignment makes at least one of the literals, the x's, true. Say it makes xi true. Then we can assign y sub j the truth value true for j less than I minus 1, and assign y sub j the value false for y equal to or greater than I minus 1. For this truth assignment, the clause with xi, that is this one, is made true by xi. All the previous clauses, those there, can be made true by their unnegated y's, and all the later clauses, all of these, are made true by their negated y's. Conversely, suppose that there is a truth assignment that makes all the new clauses true but makes none of the literal x's true. Assuming that no x's are true, the fact that the first clause is true, that is this, says that y sub 1 must be true in this hypothetical truth assignment. And then the second clause says that since x sub 3 is false, and not y sub 1 is already known to be false because we had to make y1 true, that means that y2 must be true. We can reason the same way to show that all the y's are true. But then the last clause, this, which has only false x's and a negated y, must be false. We have shown that when we convert one long clause of the input to a sequence of clauses with 3 literals per clause, the satisfiability or non-satisfiability of the expression is preserved. We can repeat this argument for every long clause, thus converting the original expression to an expression with at most 3 literals per clause, and that is satisfiable if and only if the original is. Technically, we are not done, because the original expression could also have clauses that are too short. For a clause with only one literal x, we introduce 2 new variables, y1 and y2, and replace one clause by the 4 clauses shown. Notice that the y's appear in all 4 combinations, so if x is false, one of these 4 clauses will be false, no matter what truth values we assign to the 2 y's. For example, if y1 is true and y2 is false, then this clause will be false whenever x is false. But conversely, if x is true, then all 4 clauses are true regardless of the truth values of y. And don't forget that these introduced y's are new. They appear in no other clauses, just like the y's we introduced to split apart the long clauses. And the final case is a clause with 2 literals, say w and x. For this clause, we introduce one new variable y and replace w plus x by 2 clauses, one with a non-negated y, the other with a negated y. The same argument as for the clause of a single literal applies here. If a truth assignment makes both w and x false, then one of the 2 new clauses will be false. But if the truth assignment makes at least one of w and x true, then both new clauses can be made true. The conversion of the clauses from the input CNF expression to clauses in 3CNF takes only linear time in the length of the input sequence. That is, we run through each long clause, generating new variables and new 3 literal clauses as we go, taking time that is proportional to the length of the original clause. The constant of proportionality may be large, but the algorithm is still linear. Well, we have to be careful, as always, to remember that there is a finite alphabet involved. That means when we create new variables, the y's, it may take log n time to write down their numbers, so the algorithm really could take order n log n time to generate the output expression. But as always, we'll ignore factors of log n. They cannot take us out of the polynomial class. We thus have a polytime reduction from the problem CSAT to the problem 3SAT. And since CSAT was shown NP-complete by the modified construction in Cook's theorem that produced the CNF expression, it follows that 3SAT is also NP-complete. Now it's time for the payload of the theory of NP-completeness. We're going to see some perfectly ordinary problems, not apparently related to computation in any way, that are also NP-complete. Of course, we can cover only a tiny fraction of the problems that are known to be NP-complete. But the methods, ways of designing reductions, are the things to take away from this discussion. If you encounter a problem in your work and can't come up with an efficient solution, there is a good chance that you can devise a reduction that proves it NP-complete. That proof guides your thinking. You need to consider, for example, whether you need to solve the problem in all its generality, or whether a simpler special case would give you what you need. You need to consider efficient algorithms that offer an approximation to what you really want. Without the assurance that the problem is NP-complete, you are less likely to want to attempt, or to justify to your boss, taking one of these simplifying steps. But before moving on to reductions that show the problem's node cover and knapsack to be NP-complete, we introduce one more nuance into the theory. NP-hard problems are those that would be NP-complete if only they were in NP, but that are probably or certainly harder than anything in NP. We talk about the tautology problem, which is an example of such a problem, even though it is very closely related to the problem SAT. We are ready to reduce 3-SAT to a number of other problems, thus showing each of them NP-complete. These reductions can be directly from 3-SAT or from another problem that we previously proved NP-complete. Remember, the key issue is that each reduction must be in polynomial time. However, in most cases, the construction is computationally simple, so as long as the output is of length polynomial in the input, it will be easy to argue that the running time of the transducer is polynomial. Of course, if a problem is NP-complete, it must be in NP. Usually this part of the proof is quite simple, since a non-deterministic polytime Turing machine can use its non-determinism to guess a solution in linear time and then check that it has guessed a solution using some polynomial amount of time. However, there are some interesting cases where we can only show a problem to be NP-hard, meaning that if it is in P, then P equals NP, but the problem itself may or may not be in NP. A curious example of an NP-hard problem is the tautology problem. A Boolean expression is a tautology if it is true for every truth assignment. For example, this expression is a tautology. Every truth assignment makes x either true or false. So one of the first two terms, that is this or that, will have to be true, and therefore the whole expression is true. We don't even need the term y and z. If you look at Cook's original paper on NP-completeness, he was really trying to argue that tautologies required exponential time to recognize. Because tautologies are the theorems of logic, that's what logicians care about, not satisfiable expressions. Cook was able to reduce all of NP to satisfiability, but that is enough to show that if there were a polytime algorithm for tautologies, then P equals NP. We'll address this point in a few slides. In fact, there is good reason to believe the tautology problem is not an NP. On the other hand, its complement, the non-tautologies, including those inputs that don't make sense as Boolean expressions, is an NP. We use the non-determinism to get a truth assignment and evaluate the expression in polynomial time for this truth assignment. If the value is false, then the non-deterministic machine accepts its input. On the other hand, if the non-deterministic machine accepts whenever it finds the value to be true, it accepts the satisfiable expressions, not the tautologies. The class of languages called co-NP is those languages whose complement is an NP. For example, we just argued that the tautology problem is in co-NP because the non-tautologies are in NP. Okay, now P is closed under complementation. We didn't prove this exactly, but it is easy to show because if I have a deterministic Turing machine that halts within P of n steps for some polynomial P of n, we can modify it to accept the complement language. Just have the new machine simulate the original. It halts without accepting if the original machine accepts, and it goes to a new accepting state if the original halts. Since the complement of every language in P is also in P, it is surely an NP. That proves the class P is a subset of co-NP as well as of NP. Another important connection is that if P does equal NP, then P also equals co-NP, and therefore NP and co-NP are equal. However, it is possible, but unlikely, that NP and co-NP are the same, but that they are bigger than P. We can prove the tautology problem to be NP hard. For the proof, suppose there is a polytime algorithm for the tautology problem. Then given a Boolean expression E, convert it to not E, which takes only linear time since all we have to do is add not and a pair of parentheses. Now notice that E is satisfiable if and only if not E is not a tautology. So use the hypothetical algorithm for the tautology problem to tell whether or not E is a tautology in polynomial time. Then just complement the answer. That is, say E is in SAT whenever the answer you got is that not E is not a tautology, and say E is not satisfiable whenever not E is found to be a tautology. That would be a polytime algorithm for SAT, which would show P equals NP. That is all we need for proof that tautology is NP hard. Now let's meet a real problem from operations research that CARP proved to be NP complete. A node cover for a graph is a set of nodes of that graph such that every edge has at least one of its two nodes in the set. We need to express the problem of finding the smallest possible node cover as a yes-no problem. We do so by asking whether, given a graph G and an integer k, does G have a node cover of size k or less? This is the formal problem or language called node cover. Notice that if we had a polytime algorithm for the minimization problem, that is, given a graph, find a node cover of smallest size, then we could prove that the formal problem node cover was in P. Just use the hypothetical polytime algorithm to find a smallest node cover, count the number of nodes in the cover, and see if it is at most k. That means that once we prove the formal node cover problem, or the yes-no version of the problem, to be NP complete, we also know there is no polytime algorithm for the minimization version unless P equals NP. Here's an example of a graph. One of the interesting things about NP-complete problems, and node cover is one such, is that even small instances of the problem seem hard. So how small a node cover can we find for this graph? Do you see the answer yet? Well, we'll work it out. We have to pick either C or D for our node cover, or else the edge CD isn't covered. We may as well pick C, because C covers every edge that D covers, and more. We also have to pick either A or E, else the edge AE is not covered. But picking C and either A or E does not cover the edge BF, so we need at least 3 nodes in the cover. But here's one example that works. B, C, and E together cover all the edges. Thus, given this graph and the budget k equals 3, the answer is yes. The same answer applies if the instance of node cover in this graph is this graph with a higher budget. However, if we are given this graph with a budget 2 or less, the answer is no. We're now going to prove node cover to be NP complete. Okay, we'll give a polytime reduction from 3SAT. Given an instance of 3SAT, we construct a graph. There is a node for each literal of each clause, so the number of nodes is 3 times the number of clauses. It helps to imagine the nodes arranged in a rectangle, where the columns correspond to the clauses. Each column has 3 nodes, 1 for each of its clauses. There are vertical edges connecting each pair of nodes in a column, and thus there are 3 vertical edges per column. There are also horizontal edges that connect nodes in different columns. 2 nodes are connected if they represent literals with the same variable, and exactly one of those literals has that variable negated. And finally, the budget k is twice the number of clauses, which is also exactly 2/3 of the nodes. So here's an example of an instance of 3SAT with 4 clauses. We'll construct the graph that has a node cover of 8 nodes if and only if this expression is satisfiable. So here's the column for the first clause. The literals of the first clause are x, y, and z with no negations. So those are the labels of the 3 nodes in this column. And similarly, we construct a column for each of the other clauses. It is convenient that all 4 clauses have the same 3 variables in order, either negated or not. So this graph is going to turn out to be easier to understand than might be the case otherwise. Now we add the horizontal edges. For example, in the top row where all of the x's are, each node labeled x is connected to each node labeled not x. Again, because all of the x nodes line up and the horizontal edges are truly horizontal. In more complex examples they would not be, although they always go between columns. Similarly, we see connections in the second row between nodes y and nodes not y, and in the third row are the edges between z and not z. And the final part of the output is the budget k. Since there are 4 clauses, the budget is k equals twice that, or 8. The first thing to observe about the constructed graph is that a node cover must have at least 2 of the 3 nodes in every column. If it has only 1 node in a column, then the vertical edge between the 2 unselected nodes will not be covered. And if the node cover has 0 nodes from a column, then all 3 edges in that column will be uncovered. But the budget is exactly twice the number of clauses. So if all 3 nodes in one column were in the node cover, then some other column would be shortchanged. It could get only 1 node and we would not have a node cover. The conclusion is that there can be no node cover with fewer than k nodes, and if there is a node cover of exactly k nodes, then these k nodes must be exactly 2 from each column. We're going to show that there is a tight relationship between the node covers and the truth assignments, and this connection goes through the nodes that are not selected for the node cover. That is, a satisfying assignment for the 3-sat instance will yield a node cover if we omit from the node cover one of the nodes from each column that is made true by the assignment. And conversely, a node cover with 2 nodes per column will give us a satisfying assignment by making all the literals whose nodes are uncovered to be true. We'll prove all this in a minute, but first an example. For example, here's the 3-sat instance we saw earlier, and here's the graph with budget 8 that we constructed. Here's a truth assignment. It happens to be a satisfying assignment, so we can pick a node from each column that is made true by the assignment. Here's one such choice. There are others. For example, in the first column we could have picked y instead of x. I claim that if we take the other 2 nodes from each column, we get a node cover. Surely all the vertical edges are covered since we have 2 nodes in each column. But what about the horizontal edges? Suppose we have a horizontal edge, say with x at one end and not x at the other, and neither end is in the node cover. That means both were selected as the literal that made their clause true. But how could that be? They can't both be true in any one truth assignment, so they can't simultaneously make their clauses true. We need to show that what we described is a polytime reduction from 3-sat to node cover. It is easy to see that transducer takes polynomial time. It works clause by clause, generating no more nodes than there are literals. The vertical edges can be generated at the same time, and they number only 3 per clause. The horizontal edges can be generated easily if we list all the nodes labeled by each literal. After seeing all the clauses, we can generate horizontal edges. For each variable x, we look at the list of nodes for literals x and not x. We generate edges for all pairs, 1 from each list. The total number of edges generated is no more than quadratic in the length of the input, and the edges can be generated in constant time each. We also need to show the reduction is correct, of course. That is, if we construct graph G and budget k from the 3-sat expression E, then G has a node cover of size k or less if and only if E is satisfiable. For one direction, suppose E is satisfiable and let A be a satisfying truth assignment. The argument that G has a node cover of size k is really just the argument we gave for our example earlier. That is, we begin to construct the node cover by selecting for each clause of E one of the literals that truth assignment A makes true. We know there is one because A is a satisfying assignment, and the only way to make a 3-sat expression true is to make each clause true. Then the node cover consists of the 2 unselected nodes from each column. Notice that some of these nodes may also have their literal made true by assignment A, but it doesn't matter. The important thing is that the unselected nodes all correspond to true literals. This selection of nodes has exactly k nodes, since k is twice the number of clauses. So if we can prove it is a node cover, then we have shown that G has a node cover of size at most k, in this case exactly k. We claim the nodes we selected include at least one end of each edge, so indeed we have selected a node cover. First, consider the vertical edges. We selected 2 nodes from each column. There are only 3 nodes per column, so only one is unselected. Thus, any edge in that column has at least one selected end. And how about the horizontal edges? Okay, each horizontal edge has ends corresponding to literals x and not x for some propositional variable x. The truth assignment A has to make either x or not x false. Whichever is false could not have been selected as the literal that makes its clause true. Therefore, it is surely selected for the node cover. That means every horizontal edge is covered, and the k-selected nodes do indeed form a node cover. The converse also follows the outline of the proof we gave in our example. So, suppose G has a node cover with k or fewer nodes. Since all the vertical edges must be covered, there must be at least 2 selected nodes in each column, because one selected node can cover only 2 of the 3 edges. We claim that from the nodes not selected for the node cover, we can figure out a satisfying assignment for E. If there is an unselected node corresponding to literal x, then make propositional variable x true in the truth assignment. If there is an unselected node corresponding to literal not x, then make x false. We'll see why this works on the next slide. Well, what could go wrong? We might have made a truth assignment that makes some variable x be both true and false. That is, nodes corresponding to both literals x and not x might have been outside the node cover. But that can't happen because there is a horizontal edge between these 2 nodes. And therefore, at least one is in the node cover. Thus, we do have a consistent, satisfying assignment, and the expression E is in 3 sat whenever G has a node cover of size up to k. Now, let's revisit our old friend the knapsack problem. We're going to prove knapsack is NP-complete. But it is easier first to reduce 3 sat to a variant of knapsack, which we'll call knapsack with target. That is, given a list of integers L and an integer target k, is there a subset of L that sums to exactly k? Once we've shown knapsack with target NP-complete, we'll reduce it to the real knapsack problem, which is given a list of integers L, can we divide L into 2 parts whose sums are the same? We have to show knapsack with target is an NP, but that, as usual, is an easy argument. Just use the non-determinism to guess a subset of L, then compute the sum of the integers in the guessed subset, and accept if that sum is exactly k. We're going to reduce 3 sat to knapsack with targets, so suppose we have an expression E in 3CNF and a target k. Let E have C clauses and V propositional variables. We're going to think of the integers in the list L we construct as written in base 32. We can write them in binary, so we need 5 characters per digit, but the factor of 5 is of no importance if we are only worried about performing the transduction from 3 sat instances to knapsack instances in polynomial time. The length of each integer will be C plus V, so each integer could be as long as the entire expression E. There will be 3C plus 2V integers. That means the length of the output could be on the order of the square of the length of the input. But that's okay, it's still a polytime transduction as long as we can generate the integers in time proportional to their length, which we can. Here's a picture of some of the base 32 integers we will use, those for the literals. Notice that each digit will be either 0 or 1, but the base is still 32. We need a base that large to avoid carries from place to place when we add integers. The high order V positions represent the variables. We'll have one integer for each literal xi or not xi, and thus there will be 2V such integers. The integer has a 1 in the ith position from the left end of the first V positions if it corresponds to a literal based on propositional variable xi, that is, it's either xi or not xi. The C low-order positions correspond to the clauses. The integer for a literal will have a 1 in the position for each clause that it makes true, and all other positions in this integer hold zeros. There will also be 3 integers for each clause. The integers for the ith clause have, respectively, the base 32 digits 5, 6, and 7 in the ith position from the left end. All other positions are 0. So here's a tiny example. There are two clauses and three variables in this expression, so c equals 2 and v equals 3. Let's number the three variables x, y, and z by 1, 2, and 3 respectively, and number the clauses 1 and 2 in the order in which they appear. Let's see the base 32 integers constructed for this example. Okay. First, consider the literal x. There are three variables, so the first three positions correspond to the variables. X is the first, so its position is at the left end of the first three positions. That's here. Thus we see a 1 there and 0 in the first two positions. The last two positions correspond to the two clauses. When x is true, both clauses are made true, so we have 1s in each of the last two positions. Now consider literal not x. The first three positions are the same as for literal x, but not x doesn't make either clause true, so the last two positions are both 0. That is, these. Here are the integers for y and not y. Among the first three positions, they both have their 1s in the middle, as they should. Y makes the first clause but not the second true, so it has a 1 in the low order position, and that's the one that corresponds to the clause 1, and it has 0 in the second from last position. These digits are switched for the literal not y, because not y makes the second clause true but not the first. And here are the integers for z. In the three high order positions, they each have 1 in the highest position, as that. And like y, z makes the first but not the second clause true, so the two low order positions look like the previous two integers. That is, these are like those. Now let's look at the integers for the clauses. For clause 1, we have integers with 5, 6, and 7 in the low order position. And for clause 2, we have the same digits in the second lowest position. We'll pick the target as shown. Note that k in base 32 is v1s followed by c8s. Thus it is easy to write down in time proportional to the length of the input to the transducer. We claim that when we add a subset of the 2v plus 3c integers, there cannot be any carries from one place to the next higher place. We'll see why on the next slide. In the high order positions, only two integers have a 1 in any position, so there can be no carries there. For the low order positions corresponding to the clauses, each position has integers with 5, 6, and 7 there. Even if all three are in the selected set, that's only 18, not enough. But what other integers could contribute to a low order position? Only the three integers for literals that appear in the clause that corresponds to that position. But these three integers only have 1 in that position, so the maximum sum in any position is 21. So there are no carries. But we could have made the base 22 instead of 32, but 32 is easier to convert to binary, so we went with 32. The important consequence of no carries is that the target can only be met by making each position in the sum match the corresponding position of the target. We'll see how this connects satisfying truth assignments to knapsack solutions in the next slide. First, consider the high order positions, the positions for the variables. If the sum of a set of integers matches the target, then the sum must be 1 in that position. That means either x or not x is true for each propositional variable, but not both. That in turn means that the selected integers correspond to a truth assignment. Now let's look at the low order positions for the clauses. The target has 8 in that position. We can't have 2 or 3 of the integers that have 5, 6, or 7 in that position. The sum would be too great. The only way we're going to have integers that sum to 8 in position for a clause is if between 1 and 3 of the integers corresponding to the literals of that clause are chosen, and we can use one of the integers 5, 6, or 7 to make up the difference and reach exactly 8. Now we need to prove the construction we just gave works. First, I hope you see how to construct a single integer for the output in time proportional to the n, which is both the length of the input expression e, and to within a constant factor, the length of the integer itself. Since the number of integers is proportional to the number of clauses plus the number of variables, and there can't be more than n variables in an expression of length n, it is also true that the number of integers in the output is at most proportional to n. Thus, the output can be constructed in time on the order of n squared, and the transduction is polynomial time. We need to show it as a correct reduction. As always, there will be two parts. First, we'll show that if E is satisfiable, then there is a subset of integers summing to exactly k. That is, the output instance of the knapsack with target problem has a solution. Then we'll show the converse, that if there is a solution to the output instance, then the input expression is satisfiable. For the first direction, assume E is satisfiable and let A be a truth assignment that makes E true. For a subset of integers, we'll start with the integers that correspond to the literals that A makes true. That gives us the necessary one in the position for each of the variables, that is the high order positions. The integers we selected so far make each clause true, so their sum in the positions corresponding to the clauses, that is the low end positions, will each sum to 1, 2, or 3. So for each clause, add to the set of integers we're choosing the integer that has 5, 6, or 7 in that position, whatever is needed to make the sum be 8 in that position. Now we have a set that sums to 1 in each of the high order positions, that is the positions for the variables, and to 8 for each of the low order positions, that is the positions for the clauses. That sum is exactly the target, so there is a solution to the output knapsack instance. Now we must show the converse. Assume the output instance has a solution, a subset of its integers whose sum is the target. First, look at the high order positions, those corresponding to the variables. The subset of selected integers matches the target, so it has 1 in each of these positions. The only way that could happen is if we select exactly one of the two integers for the variable corresponding to that position. If x is that variable, that means we picked either the integer for x or the integer for not x, but not both. That means we have a truth value for each variable x. If we pick the integer for x itself, then make x true, and if we pick the integer for not x, make x false. Either way, the literal for the integer we picked is true in this truth assignment, which we'll refer to as a in what follows. Now, look at the position for one of the clauses. We discussed earlier that with only 5, 6, and 7 available for a given position, we have to pick exactly one of them if we are to reach 8 in that position. But we can only reach 8 if the selected integers for the variables have among them something between 1 and 3 ones in that position. That means the truth assignment A must make each clause true, and therefore A is a satisfying assignment. We have now proved that when an output instance has a solution, the input instance is satisfiable. That was the second of the two needed directions, so now we know the transduction is correct. The output has a solution if and only if the input is satisfiable. We're now going to prove the original knapsack problem is NP-complete. We'll refer to it as partition knapsack, but it is exactly what we earlier called just knapsack. That is, given a list of integers, can we partition them into two disjoint sets with equal sums? We'll show partition knapsack to be NP-complete by reducing knapsack with target to it. Remember, we already saw that partition knapsack is an NP, but if you forgot, just guess the partition and sum the two sets. Here's the essence of the reduction from knapsack with target to partition knapsack. Suppose we're given an instance of knapsack with target, say the list L and target K. The first thing we need to do is compute the sum S of all the integers. That takes time proportional to the input length n. Now we can make our output, which is an instance of partition knapsack. This output is a copy of the list L followed by 2 or more integers. One of those integers is 2k, that is twice the target, and the other is S, the sum of all the integers on list L. Here's an example of a knapsack with target instance, the list L consisting of the integers 3, 4, 5, and 6, and a target of 7. The resulting instance of partition knapsack has the same integers, then 2k, which is 14 in this case, and finally the sum S of 3 plus 4 plus 5 plus 6, which is 18. This instance of knapsack with target has a solution. We can select the integers 3 and 4 from L. Their sum is the target 7. The output instance of partition knapsack also has a solution. Take the integers in the solution to the input instance, that is 3 and 4, and include the last integer, the sum of all the integers on list L. Notice that both the selected integers 3, 4, and 18 and the unselected integers 5, 6, and 14 sum to 25, which means we have a solution to partition knapsack. That turns out not to be a coincidence. Including the integer that is the sum of L always turns a solution to the input instance into a solution to the output instance. We'll see that when we prove the correctness of this polytime reduction. So here's the proof of correctness. First, observe that the sum of the integers in the output instance of partition knapsack is 2 times s plus k. That is, the integers on list L sum to s, and there's another integer s in the output list, so that makes 2s. And then there is an integer 2k in the output list, which makes 2s plus 2k. Therefore, if we are to partition the output list into 2 parts, each part must sum to s plus k. First, suppose the input instance of knapsack with target has a solution. That means there is a subset of L that sums to k. In the output instance, we can pick this subset of L plus the integer s to sum to s plus k. Of course, what remains will also sum to s plus k, so we have a solution to the output instance. And conversely, suppose there is a solution to the output instance. We claim that the two integers s and 2k cannot be in the same partition because their sum is s plus 2k, and that's more than half the sum of all the integers in the output instance, which recall is 2s plus 2k. Now, if the output instance of partition knapsack has a solution, then the subset of L that is in the same partition as the integer s must sum to s plus k. That's half the total. That means the subset of L sums to exactly k. Now look at the input instance of knapsack with target. We just showed that there is a subset of L that sums to k, so this subset is a solution to the input instance. That completes the proof that the input instance has a solution if and only if the output instance has a solution. We therefore have a valid polytime reduction from knapsack with target to partition knapsack, and we now know the partition knapsack problem is also NP-complete.